without further ado, I'm going to introduce our speaker. Our presenter today is Dr. Gary Hawkins. Dr. Hawkins is excited to present about some interesting topics, including how to observe the universe from the backyard and the probability of existing aliens. Dr. Gary Hawkins got his doctorate in satellite communications at the University of Bristol, the same year the Hubble telescope was launched. Having worked in the telecommunications sector for all his career, he is now taking time to write, travel with his family, raise a 5-year-old, and pursue hobbies like astronomy. Gary's main cosmic interest is electronically assisted astronomy, a relatively new branch of amateur astronomy that is particularly well suited to the public outreach. And so, without further ado, let's welcome Dr. Gary Hawkins.
Thanks everybody for joining. Anthony did such a great job of the introduction there. I'm not sure there's much else to say. But as he's in the telecommunications sector for about 30 years, I'm now, if you like, retired, and I'm pursuing other more interesting topics. One of those is astronomy. So I have a couple of unusual things. I am a professional house sitter. So I actually travel the world and house sit properties. I particularly like farms, so something unusual about me. And the third picture, the one at the bottom there on the introduction slide that hopefully everybody can see, that's where I did my PhD. That is Goonhilly in the UK. It's one of the largest Earth station receiving centers in the world. And I worked on Goonhilly 10 while I did my PhD in, from 1990 through to 1994. As Anthony rightly said, I started my PhD that Hubble launched. I'm also a member of the San Diego Astronomy Association. I'll give you a little bit more information about that. I'll try and make this as interactive as possible as we go forward. So perhaps the first thing you guys can do is in your chat window, can you just type in your ages so that I can get a rough idea of what sort of age range we've got online? And so my presentation today is called Where Have All the Stars Gone? For reasons that will become obvious. And it seems to be that we're kind of mainly in the middle school range here at the moment. If my middle school, I'm not really, I got a 5-year-old, right? I don't know a lot about kids apart from those up to the age of 5. All right, so without further ado, let's see if I can roll this presentation forward. So if you were around a few hundred years ago to when man sort of first looked at the sky that you would have seen then is kind of completely different to the sky you see today, which is somewhat of a shame. Even into the sort of late 1700s, 1800s, before really the invention of the electric light bulb, you know, most people, if they went outside and looked up, they would have seen a sky full of stars, and they would have seen the Milky Way across that sky, and it was and is a spectacular sight. I've actually just spent 5 months in New Zealand traveling, and I'm put out a quick social media call here for anybody, and apparently Carl is online. And he's 61. So good evening, Carl, from Birmingham in the UK. You would have looked up at the sky and you would have seen the Milky Way and thousands of stars. And that's because our eyes are actually reasonably sensitive to the stars. We can see down to 6.5 magnitude stars. The brightest stars in the sky are 0 magnitude stars. Isn't it? As you go up in number, so like 1 magnitude, that's 2.5 times dimmer. If you go down 5 magnitudes, that's 100 times dimmer. So 6.5 is, you know, something over about 300. And with a dark sky, you can see that. And so that allows you to see thousands and thousands of stars in the sky, which is pretty spectacular. How many of you have actually been able to, how many of you have seen the Milky Way? Has everybody seen the Milky Way? Maybe the easiest way is, if somebody hasn't seen the Milky Way, can they type no in the chat window, please? If you've never seen the Milky Way, I would suggest that you head out to somewhere like Palomar or Borrego, or one of the best places locally to go see stars is Death Valley. It's absolutely spectacular right there. And like I just said, I was actually in New Zealand for 5 months recently. And it's so dark in the majority of New Zealand that you literally see the Milky Way every day. It was incredible. So I saw one no there. So Claire, I believe, has never seen the Milky Way. So Claire, I think you, if you want to see the Milky Way, you need to ask your parents if you can take a trip out to Anza Borrega. And because the stars were so obvious and apparent to everybody, they were really important to ancient man. And early cultures, from the Mayans, the Egyptians, Indians, Chinese, Greeks, the kind of list goes on. But the cultures that developed technology and stuff first and early, the stars in the sky were very important to them. One thing was associated with religion. People associated gods and spirits and other celestial bodies and sort of weaved it into their religion. People soon realized that the night sky is regular and apparent and repeats itself on a yearly basis. And so the night sky became a very important tool for predicting things like the agricultural seasons and floods. Sirius is called the dog star, and you may have heard the saying, dog days with summer, and that's associated with the fact that as Sirius begins to set in the night sky, that's typically when the summer is ending. The night sky was also a very important navigation tool for early people, particularly mariners. If you've probably heard of the star Polaris, it's due north. So if you know where Polaris is, then you know in which direction the points of the compass are. So it was a very important tool to early mariners. And for people like the Greeks and stuff, as they began to see the periodicity in what they were seeing overhead, it became the basis of a lot of the early mathematical theories that were developed. So the night sky was extremely important to ancient man, and unfortunately it seems to be something that we've perhaps lost a little bit now. And the reason for that, quite simply, is light pollution. After the invention of the electric light and with the development of civilization, we have built out cities across most of our land. And obviously in cities, you have buildings with lights and street lights and car lights. And that creates something called sky glow. And that sky glow effectively masks the magnitude of the stars that you can see in the night sky. And so if you look up from San Diego into the night sky, even on the best of nights, you can probably only see down to about magnitude 3 stars, and that's several hundred stars. So while there are still a few stars in the sky, and you obviously see the moon, and recently we've got Jupiter, Venus, and Jupiter, Saturn, and Mars in the night sky. You know, you really lose that impact that that the early man saw from the wonderful sight when he looked up at the night sky. And light pollution is measured on something called the Bortle scale. You can read a little bit more about it if you're interested at the following website. But basically, it's a 1 to 9 scale that describes how bad the light pollution is in your particular area. And we are Bortle 8 here in San Diego, which is pretty bad. And if you look at the map there, you can see that, if you live in any of the built up areas in America now, light pollution is really bad. The red and the orange is very bad. And so, you know, many people just don't see what early man saw. And this is sort of a more detailed look at our light pollution locally. I'm located fairly close to the city of Poway in this red area. It's called the red zone, which is a Bortle 8 area. The city center is Bortle 9, so is Tijuana. And really, in order to get to some decent night skies, you kind of have to head out east of us towards Anza Borrega. And there's some really quite decent dark sky areas in Anza Borrega. And in particular, there's a place called the Little Blair Valley, which is a designated dark sky area here locally. And I guess you can tell one of the roads is called Telescope Road. So I guess that kind of illustrates that a lot of people go out there to do viewing. The club that I'm a member of, we have a viewing area here. It's in Tierra del Sol. So at least it gets you away from the majority of the bright lights, and a lot of our club members will go out there and set their telescopes up. So, having said that we've got a problem, how do we solve that problem? Unfortunately, we can solve that problem, even if you live in the city. So there are 3 things that you can do at the sensor, which if you're just looking up at the sky is obviously your eye. But, you know, if you use a camera, for instance, it's just as applicable to a camera. So my question to everybody is, can you think of one or more of these 3 things that you can do at the sensor to allow you to see more? So I'll take answers on chat or on a video, on speech, if you guys want to shout some answers out for 10 to 15 seconds. And there was total silence. Do we have 24 people online here? Come on, people, wake up. Anybody? Anthony, come on. Emily. Go for it. Tell me what you can do at the sensor here to allow you to see more. This is kind of basic physics. Okay, well, we're not getting eat carrots. Okay, there's a good answer. I like that one. Okay, somebody's got a sense of humor. Paul, thank you for throwing that comment. Vitamin B. Okay, you guys are obviously use a telescope. Okay. Yeah, that's kind of where I'm going with this, but I'm kind of thinking more eat broccoli. All right, we're getting lots of vegetable and vitamin related comments here. Anything else? At the sensor, come on, I'll give you a clue. If you're an owl and you fly around at night, okay, what do you have fairly big ones of? And it's not wings, and it's not glasses either. Yeah, okay, all right, eyes, yes, thank God somebody came up with the right answer. Okay, so there's 3 things you can do at the sensor. The first is you make the aperture bigger, and the size of your pupil, the size of your eye is obviously the aperture. So yes, owls, dormice, they have big eyes, right? Because they need to see in the dark. So yes, we can make the aperture a lot bigger. We can do a couple of other things. We can make the sensor more sensitive. And we can do that in a number of ways. It's a bit difficult with your eye to make it more sensitive, but if you've got a camera, for instance, you can cool that camera. You can actually reduce the thermal noise in the camera by cooling it. And so the camera that I use on my telescope has a, I can't remember the name of the actual cooling mechanism now, but it has a cooling mechanism on it which takes it down to about -5 degrees. So that helps. And then the final thing you can do at the sensor itself is that you can integrate with time. If you allow more photons to build up over a period of time before you actually take that final image, if you can think of like water pouring into a bucket, the number of photons that you get on any particular sensor. Yes, PTA. Thank you for that, the cooler answer. Will actually allow you to collect more light and therefore see more things. So those are the three things that you can do as a sensor. You can also do a couple of other things which kind of help as well. You can filter out unwanted light. And so you'll see when we get to a picture of my telescope that I actually have a filter in the optical chain that filters out sodium and mercury vapor light, which is one of the light, well, it was with the older street lights. They emit that type of light pollution and it basically cuts it out. The other thing you can do is to move to a dark sky location. You can move to away from the city and out into the countryside where it's dark. And another thing you can do is you can move up in the Earth's atmosphere. So that's why you find that all of the big telescopes are actually located in remote areas, high up on mountains, because the less atmosphere you've got between you and the stars you're trying to view, the clearer picture you will actually get. And of course, you can take that to the extreme, right? You can take your telescope up into space, and that is an animation of the Hubble Space Telescope. So telescopes like Hubble have allowed us to really gain an incredible view of the universe. Hubble's actually fairly big. You can see that isn't a real picture, by the way. You can actually see the Hubble compared to a standard size bus. It's pretty good. So here's another question, maybe a little bit too early for most people on the phone. But when Hubble was launched, there was a lot of press and notoriety and everybody was really excited. And they got it up into the sky and switched it on and started looking at the images. And all of a sudden they realized that something was badly wrong. Does anybody know by any chance what was wrong with Hubble when it originally launched? You can type it in chat or give me a quick shout out there on your audio. So Peter said no. Okay, so I'm looking for somebody with yes. Anybody? The camera was damaged. No, but close. Cap didn't get taken off. Yeah, I like that one. No, they took the cap off. The mirror was cut incorrectly. Very good, yes. And yes, the mirror was actually incorrectly ground. Now, we're not talking inches here, or in fact, we're not even talking millimeters. We're talking fractions of a millimeter. I think it was actually down in the sort of nanometer type range. But the mirror was actually polished incorrectly. The algorithm they were using in the polishing machine was incorrect. And so when they got Hubble up into space for the first time and started taking pictures, they got some great pictures, but unfortunately, they weren't as clear as they were kind of expecting. So what do you do at that point, right? You've got a whacking great big telescope up in space. You can't bring it back. You can't change the mirror. So what do? So actually they reversed engineered the problem, and with some very clever mathematics, they actually came up with a correction optical chain that they put into the telescope. They had to take out one of the other pieces of optical equipment to make room for it, but they did actually manage to correct it. And now Hubble, of course, produces some fantastic imagery. And if you're interested to see what Hubble does, the Hubble website is on the screen there. Okay, so before we talk about some visual observing and some of the stuff I do, so one of the questions we need to ask ourselves is, how big is the universe? Because unless you understand the sort of context of the size of the universe, it's very difficult to kind of grasp some of the things that, you know, we're talking about in terms of how far things are away. So, anybody recognize this guy? You can shout it out. Type it in.
Einstein.
Come on. Who?
Einstein.
Oh, Yes, correct. It's Albert Einstein. One of the most, very good, Nathan. That spoilt my slide already. Thank you for that. Well typed. E equals mc squared. So yes, Einstein, one of the most brilliant scientists of our generation. Kind of a quirky man. Oh, we're getting clever. Nathan, very good. You're just spoiling this slide for me, aren't you? Maybe I should hand the mic over. So yes, Albert Einstein came up with the theories of general and special relativity, which basically is a set of mathematical guidelines that kind of define how we understand space today. And one of the important things that he did as part of this, yes, energy equals Minecraft squares, very good. You do realize I'm too old for Minecraft, right? So one of the things that he did define was a new distance reference. Can anybody tell me what that distance reference is? Nathan? Or anybody else? Abigail? Close enough, a light year. So Einstein developed, as part of these things, one of the things he developed was the speed of light. He worked out essentially how fast light could travel. And the speed of light is 3 times 10 to the 8 meters per second, or 300 million meters per second, or 300,000 kilometers per second, or about 186,000 miles per second. Light basically can travel pretty damn quick. And we need that. Fortunately, we use this as
Minecraft captures squared.
Okay, was there a question there? No, we use the light year as a new distance reference when we talk about space, for reasons that will become apparent in a minute. Because you can't use, and yes, we do use the parsec as well, but I'm not going to go down that road at the moment. For reasons that will become apparent in a minute, because space is huge, and if you use meters or kilometers or miles, it just doesn't work. So you have to do something else. And so we're going to talk about the light year. And it's a universal physical constant. It's a constant that does not change. And as Nathan correctly pointed out earlier on in the presentation, Einstein came up with the very famous and simple equation E equals mc squared, which basically says that matter is interchangeable with mass. So a light year. How big is a light year? So let's try and scope this out for you. So the sun, the closest star that we have from us is Alpha Centauri, which is a triple star system. It actually consists of 3 stars. It looks like a single star when you look at it through a telescope, or at least I think it does. I'm not really a star person. I'm more interested in deep sky objects. But it's a triple system. It consists of Alpha Centauri A, Alpha Centauri B, and a much dimmer third star called Proxima Centauri. And this triple system is the closest star to us. It's 4.3 light years away, and I'm going to illustrate how far that is in a minute. The average star in our galaxy is at least separated by about 5 light years. And there are about 250 million stars in our galaxy, probably more. There's a lot of space out there. But I'll try and give you an idea of how big that is in a couple of seconds. But just before I do, the moon is 1.3 light seconds away. So it takes light 1.3 seconds to get from the moon to Earth. The sun is about 8.3 light minutes away. So the sun's energy takes about 8.3 minutes to come across the distance between us and it and bathe us in sunlight. And Jupiter, its closest point to Earth, is about 33 light minutes. Now I'm going to try and give you some idea of what that means now with the next slide. Oh, and before I do, then this is the reason you don't use kilometers, because if you express that distance to Alpha Centauri in kilometers, you get a very large and difficult number to deal with. So if we take our solar system, and I think most of you, right, have probably got a good idea of perhaps the size of the solar system, right? Yeah, you understand that the Earth and the other planets rotate around the sun, that the closest planet is Mercury, the farthest planet away, if you don't class Pluto as a planet, is Neptune. And it's a pretty big body, right? I mean, you know, it's pretty big. But let's just try and imagine, right, taking the solar system and compressing it down, right? And we just keep compressing and compressing and compressing. And we're going to compress it down as small as a 1 cent piece. So I've now taken the entire solar system and I've compressed that down to a 1 cent piece. So the sun would just be a speck in the middle of that 1 cent piece. The planets would all be circling around the sun, so small that you couldn't see them, you know, like a grain of sand or perhaps even smaller. And that's our solar system. And if you were to put that on the 0-yard line of a standard size American football pitch, and can anybody guess how far out Alpha Centauri would be in terms of either meters or feet? I'm taking guesses for about 10 seconds before I'm going to tell you. Come on, somebody throw a number out there. 100 meters. Okay, close. 20 feet. Nope. 100 meters was pretty good. The entire field, well, that's about 100 meters. Justin said 50. Okay, well, actually, it's about 65 meters. I'm more actually akin to feet. It's about 264 feet. Okay, so just try and think about this, right, for a second, and we start to gauge the size of the universe, right? So here we are. Here's our solar system. We're on the goal line, and there's nothing for 264 feet. And then there's this speck, which is Alpha Centauri. And then the next star is 5 light years, the same distance beyond that, actually a bit further. And every other star is separated by the same distance. And then in the middle of all of this, these stars dotted around all over the place, there is essentially nothing. Although with the sort of evolution of dark energy theory and stuff like that, that statement is probably not 100% true. But in terms of actually what you can see, there is nothing. It's pretty staggering just how empty the universe is. And if you kind of think how many stars then there are in our galaxy, there's a whole lot of nothing out there with these stars all dotted around. So there's some stuff going on in the chat here that I'm not 100% sure. I don't think any of these are questions that were directly meant for me. I'm just trying to see if they are, they're beyond my capability. So I'm just going to leave those for the time being and carry on. But if you've got questions, just throw them in the chat and I'll try and keep an eye on them as they go. How big would or could extend to this scale? Okay, I'm going to need, what is OORT? Nathan? Is that a misspell or Oort cloud? Huh. Okay, well, I think you're going to have to do some educating for me in a couple of minutes because I have no idea what you're talking about at the moment, although I could probably look it up. So anyway, we'll move on. All right, so where was I going? Right, so just to try and again illustrate how big things are. So the object, the man-made object which is now furthest from Earth is Voyager 1. Voyager 1 was launched in 1977 and has been an incredible success. It's been in space now for 40 years. It's flown across the solar system. It's gone way outside the solar system. It's traveling at about 60,000 kilometers per hour, heading out into space. It takes 17.5 light hours for information to come to, or come from, or go to. So if you want to tell this thing to turn right, which actually it can't actually do, but if you wanted to, it would take 17.5 hours to send the command out there. And then it would take another 17.5 hours for the acknowledgement to come back. So it would take you over a day to tell it to do something fairly simple. It is the, like I said, the farthest man-made object away from the Earth. And yet, if you were to go back to our little graphic there of the football pitch, it literally is about 2 to 3 inches off the touch line. So I think now you can start to appreciate some of the problems that we have here with the universe, and maybe that will come into play when I get to the aliens part, if I manage to get that far. One of the big problems here is that space is huge, and if you can't hear or see stuff that other civilizations are putting into space, or you don't know they're there. And this thing is the farthest thing away from Earth that we've got. So nobody's going to see that 2 inches off the touch line, right? Because nobody's there. So that's kind of interesting. Anyway, yes, Carl said, just listen to the presenter, folks. Thank you, Carl. Okay, right, going on. So here's our galaxy, known as the Milky Way galaxy. We are not in the center. In fact, we're more than halfway out on one of the spiral arms. The sun is a relatively average star in about 2 to 400 million stars, which hopefully, if my, oh, there we go. I'm just struggling here with one of the keys on my keyboard, so I'm not sure. So if I hesitate for a second, just be patient. The Milky Way is between about 170,000 to 200,000 light years in diameter. So again, going back to our picture of the football pitch here, you know, try and use that as a reference point to just how big we're talking about. And that's just our galaxy, right? There are billions of galaxies out there, and we're just talking about ours at the moment. Okay. Yep, I'm still having problems with one of my keys here. Yeah, so as I said, 250 to 500 billion stars in the galaxy. Nobody knows exactly quite how many. And our galaxy is actually part of a group of galaxies called the local group. There's about 7 galaxies in it. And in fact, one of them is on my screen. M31. M31 is actually a lot larger than the Milky Way. It's about 4 times as large. And it has 2 satellite galaxies that are actually very close to it. And when you see images of M31, and in fact, I've got one for you in a couple of minutes, you often see those galaxies as well, framed in the same image. They're M110 and M32. But in addition to that, in this local group, and they're called the local group because these galaxies are all basically moving along together, tracking together, although they are actually not all going quite in the same direction. And there's a good deal of distance between us and Andromeda, 2.5 million light years. And as I said, Andromeda is about 4 times the size. They estimate around 1 trillion stars. Whoops. And a fact that's not coming up on my screen, but should be, is the fact that Andromeda and the Milky Way will actually collide at some point. This is kind of worrying, although I think for most of us it's not going to matter because it's estimated this is going to take about 4 billion years, as Nathan correctly pointed out. If you don't come top of the cahoots thing, Nathan, I will be talking to you. Yes, correct. 4 billion years, 4.5 billion years, they might actually collide. But it won't actually probably be a collision in the sort of typical sense of the word, you know, not 2 cars crashing into each other. Stars are pretty far apart. It's going to be more of a passing through. But yes, we will be all very dead by then. So anyway, that's our local group. And while I was in New Zealand, actually, I actually got to see two of these. The night sky is so dark that you can actually see the small Magellanic Cloud and the large Magellanic Cloud. They are dwarf galaxies that are actually fairly close to us and are on the bottom right-hand side of the graphic that you're currently looking at. All right. So this is an interesting graphic, and I'm not going to spend too much time on it because I'm not a cosmologist. And it really needs a cosmologist to describe this to you. But one thing I did want to do is I wanted to describe the size of the observable universe. And if somebody really knows what they're talking about, Nathan, they may actually be able to correct me on this, because I'm not sure actually observable may not be the correct word here. But let me put it this way. We can see out only so far into the universe, and that is 13.7 billion light years. And that gets us to view something what's called the cosmic microwave background, which was discovered in the mid-60s. It's the farthest point that we can see into our universe. The light, well, actually more correctly, the millimeter wave radio waves that are coming from this particular part of space has been traveling for 13.7 billion years. It's as far back as we can see. And actually that does bring me to an interesting point here. Everything that you're looking at in space is a snapshot of history, because light takes this finite time to get to us. So everything that you see is actually a historical record of what's taking place. So when you look at the sun, or you look at the moon, for instance, that's like it was 1.3 seconds ago. If the moon suddenly exploded, which it won't, but if it did, we would actually see it 1.3 seconds after the real event took place. And much like when we see a supernova in space, if that star, when it explodes, is 1,000 light years ago, the actual explosion occurred 1,000 years ago, and it's taken that long for the light to actually reach our telescopes here on the Earth. So the size of the universe that we can see is 13.7 billion years, but that we got to remember that that's what we can see. So it's actually taken 13.7 billion years for that light to get here. So the actual universe is bigger than that. And we also know that the universe is actually expanding and it's accelerating. So the current estimates is that the dimension of the known, or of the, I would say entire universe, because a cosmologist will correct me at this point, but we know that the universe must extend about 90, in diameter must be about 96 billion light years, about 40, actually about 92 actually, about 46 billion light years in radius. So anyway, I wanted to throw that up there because it's kind of a nice graphic that kind of explains. And this WMAP satellite that you see here is actually being developed, I believe, at UCSD. A lot of the hardware is being developed there. And I listened to a pretty interesting presentation on how they're going to measure the cosmic radiation microwave background and what that's going to tell them. And WMAP is the satellite that hopefully will be put up in the next couple of years that will do that. So let's try and get back to something a little bit more real. What can we observe from the Earth? And I'm sure, as you probably know, I'm just checking my time here, so I'm probably running a little bit slowly here. So Emily or Anthony, if you want me to stop at any given point, I will. Just let me know. But anyway, from the Earth, you can see a number of things. The moon, the planets, some of the planets. We can see asteroids, meteors, and in fact, comets. And I'm not sure if any of you had the opportunity recently to see the comet. I did not. I was in New Zealand, so unfortunately I was on the wrong side of the planet to view the comet. Did anybody get to see the comet? Maybe you can just type yes in your chat box if you did. We can also see star clusters, nebulas, and galaxies. And that's kind of my interest. These fall under the general category of what's known as deep sky objects. And yes, Carl from Oceanside saw it. Fantastic. And a lot of the more prominent objects, the deep sky objects, were actually initially identified by a guy called Charles Messier. And okay, Anthony, I got that. Thanks. And he published a catalog, which was kind of interesting because he wasn't actually trying to publish a catalog of interesting objects. He was trying to publish a catalog of objects which were not comets, that kind of then got renamed to the Messier catalog, which is the big, basically the big objects that we can see from the Earth and that you can view with a telescope. So here is my telescope that I use for EAA, which is called Electronically Assisted Astronomy. It's a small telescope, relatively cheap. You can put my whole setup together for about, well, except for the camera, you can put my whole setup together for about $1,000, which is telescope scale, is pretty cheap. It consists of a 6-inch Smith-Cassegrain telescope, a focal reducer, which gives me a slightly wider field of view than I would get from the native telescope, a 9-megapixel camera, which is actually quite expensive, but you can use much cheaper cameras behind and still get some very decent results. A CCD CLS filter, which, as I mentioned earlier, filters out unwanted light. Went the wrong way. An E-finder that allows me to take a wide field view of the sky. And it all sits on an equatorial mount. So basically, as the stars move relative to the Earth, which of course is caused by the Earth's rotation, the telescope follows the star and keeps everything in its field of view. I'll skip this one, I think. And so my main interest is public outreach. I won't bore you with the links on the bottom, but when you go back, if you want to either find out when I'm doing outreach, when my club's doing outreach, or some of the outreach videos that I've already got online, just go to the links at the bottom of this thing. And that's my 5-year-old, by the way, who's quite into astronomy. And the workflow that we use for this is we basically get the camera to take an image, and the images are taken quite quickly, about every 10 to 15 seconds, but I'm integrating over time, as I kind of mentioned earlier on. And to the sensor image, we apply a dark and a flat, which corrects for hot pixels in the camera, which are basically bad pixels. That's the dark. And the flat corrects for sensitivity changes across the camera aperture. We then stack those images. Basically, we align the images and we add them together. This has the effect of increasing the signal to noise ratio, making the image better. And then finally, I'm able to actually do a little bit of processing on that image to give me a final image. So that's my workflow. And I do this all in a tool called SharkCap Pro, which runs on the same laptop that I'm doing this Zoom call on tonight. It's basically an i3 laptop. It's pretty lightweight. And these are whoops, that wasn't supposed to happen. These are some of the images that you might see. This isn't a very exciting image. This is the M39 cluster. It's an open star cluster. It's a group of young stars, about 30. But what it does show you is the field of view of my camera. It's, as I said, about 9 megapixels, 3000 by 3000 pixels. I have a field of view of just short of 0.7 of a degree. And if you were to view the moon, as I was actually last night, and you'll see on my Facebook feed at the moment, the moon appears about that big in the sensor when I view it. So it's basically, I've got a field of view that's slightly bigger than the moon. This is a much more impressive deep sky object. This is the M13 Hercules globular cluster. This is a cluster of stars that are gravitationally connected. These star clusters tend to be some of the oldest things in the universe. This particular cluster contains about 100,000 stars, actually several 100,000 stars. It's about 145 light years in diameter, so it's actually a fairly large object. And it's about 22,000 light years away from us, so some distance across the galaxy. It's a beautiful star cluster. It takes up about, well, in fact, I've got a slide in a minute. You'll see how much it takes up in the camera, but this is zoomed in a little bit. But you can see the type of definition I'm getting on the star cluster. It really is a fabulous cluster to view. This is the M57 ring. Actually, this is the M27 Ring Nebula, I think. Actually, it's M57. This is a planetary nebula. So this is a star that at some point in the past has had a fairly cataclysmic event, although it's not a supernova, and it's ejected a good amount of matter. And what you actually see is that matter radiating away from the star, which you can just about see in the center here. It's right here. And you can kind of think of this as like a stone being thrown into a pond. When that stone hits the pond, the waves radiate out in a circular pattern. And this is the wavefront of the energy that's been ejected from this star. And it's traveling outward. So with time, this will get bigger. Planetary nebula, blah, blah, blah. Fairly small target. This one's only about 4 arc minutes across, so pretty small in the field of view of my telescope. Zoomed in considerably. And this is the M16 Eagle Nebula. This actually takes most of the frame. This is a nebula, obviously. It's a beautiful object. It's kind of, many people say, most nebulas are named, or they kind of name them after what people see in them, and people see an eagle here. I'm not sure. I think if you turn this the other way up, it might look more like an eagle. But again, a beautiful example of a nebula in the sky. And if you could actually see this, if it was bright enough that you could see it, it'd be way bigger than the moon. And so it would make our night sky look incredible. And the next object, if I can remember, yes, is the one that I've got behind me, is M31. This is the center part, because this is such a big target that it won't actually fit in the field of view of my telescope. It's actually about 3 degrees wide by about 1 degree high. This is the M31 Andromeda Galaxy. So what you're seeing is the central core. You can actually see some of the dark areas here. So these are the spiral arms here of the galaxy. This is a huge target. Again, if you could actually see this, if this was in our night sky, this would be the most dominant thing in our night sky. It would make the moon look pretty small. But you can't see it. It's there. You just can't see it. It just takes some time. Right. Okay. Oh, and here is a picture of Andromeda that you won't get from my camera system, because mine is real time. I can actually do this in real time, and I do this for public outreach, and this is why I have a real time system. But if you take hours worth of data and then you're prepared to spend another couple of hours processing it, this is actually what you can get. This is some of my astro friends who do astrophotography. This is the type of image that they can get. You can actually see now M31 in all its glory. You can see some of the stars here. These are not part of M31. These are the stars in our galaxy. M31 is so far away that all we see is the light from the stars. We don't actually see the individual stars themselves. And this is one of the satellite galaxies that I mentioned, and this is the second of the satellite galaxies. And I can also do planetary imaging as well. I don't do it very often, but I can do it. But I can't do it in real time. I can image the moon in real time. But when it comes to things like the planets, like Saturn and Jupiter, you need a lot of post-processing software to start pulling this. And relative size. So I talked about relative size, what these things would look like in the night sky. Here we go. Here's the moon. Here's the M13 globular cluster, considerably smaller than the moon, but still a pretty big object. Here is M31. This thing is huge and would dwarf the moon if you could see it. The Eagle Nebula, and then the other targets that I mentioned as well. And I'm just going to play you a 3-minute video here. And Anthony, you need to make the call here. I can either stop after this 3-minute video, or I can do the 3 slides about aliens in a couple of minutes. So you make the call. But I do want to just show you this video first. This is a live stream of an EAA session from a friend of mine in Massachusetts called Corey. And Anthony said, do the 3 slides, so I will. So this is a 3-minute live stream video that's been recorded. So I'm just gonna let you listen to this, and I'll probably just throw in a couple of comments. So I'm hoping it will start. All right, hold on one second. Hopefully you can hear the volume. So Corey's going to look at M27 here. This is, or the map that was over here was what was controlling his mount. It's actually a sky map. It's a free sky map that you can get. It's really good. And what you're actually seeing here is SharpCat being used to capture and stack these images.
This is not turning.
Okay, you can't hear the audio, so
Oh my god.
So I will talk.
It disconnected.
Yeah, so this is M27 that Corey's bringing up here in SharpCat. That's a 8-second image grab with a little bit of processing on it. So what Corey's now going to do is he's going to allow his camera to grab some more images, and they will stack, and this image will get slowly better over a couple of minutes. SharpCat Pro is also a free tool. Well, it is in its basic form, which is pretty comprehensive. It's written by an English guy. And in fact, most of the software that you actually will use to do this type of astronomy is actually free. I pay for the pro version of SharpCat Pro. But basically, that's only like $15 a year. So this is another planetary nebula. The star in the center here is the one that had a cataclysmic event at some point in the past. And this is the bubble of gas that's rapidly expanding away from the, that's been ejected by the star and is now moving out into space. And as you can see, right, this is practically real time, right? And I can get a similar view from here in San Diego. And so even though I'm dealing with all this light pollution, with the EAA technology and the software that's able to support it, you can actually still do some really good viewing, albeit that you wouldn't know that those targets were there by looking up into the night sky at all. So yes, so that's kind of EAA in action. I think that's probably Corey finished. Okay, so just aliens is not my expertise at all, but I did want to leave you something fun, perhaps just to think about. So what is the probability of the existence of alien civilizations? We kind of all hope they're out there. Well, I guess some of us do. Is there anybody online that doesn't want to meet an alien? Oh, Paul said certainly out there. Okay, thank you. Anybody doesn't want to meet an alien, apart from watching a movie about one, perhaps? Okay, well, we didn't get any no's, so that's good. So, oh, not sure, Preston said. Okay, fair enough. So basically, this is kind of something that you can do a little bit more research on if you're interested. And so there's this kind of interesting equation called the Drake equation. And like I say, this isn't my speciality at all. And there may be more modern research on it, but it's kind of a fun equation, right? So Drake came up with this equation, Professor Drake probably came up with this equation that tries to estimate what the probability of there being a alien civilization out there that's actually capable of communicating with us. And so he came up with this equation, and it's got a whole number of variables in it, right? Including the rate of star formation, the fraction of stars that might have planets, the average number of planets that might support life, the fraction that can go on to, well, that might support life, then the fraction that actually go on to support life, and then the fraction that actually go on to support intelligent life, which of course is a number that's getting pretty small. And then another interesting couple of things that you took in to account is civilizations don't last that long. I mean, even the human race is not going to last that long. And so consequently, do they overlap? Because if they don't actually overlap in their existence, they're not going to be able to communicate with each other. And then I guess the thing that kind of makes it really difficult, and we go back to that football pitch analogy that I gave earlier on, is even if all of these things fall into place, right? Can we actually either hear them or see something that they've launched? And obviously launching a spacecraft like we did with Voyager 1 isn't going to do it. And they reckon that our radio waves from the Earth only go out about 100 light years, which is not very far. So there could be lots of civilizations out there all in a kind of similar situation to ourselves, right? Where they've developed technology, they're transmitting, they want to find somebody else out there in the world, but we haven't yet worked out a way that we can actually do or send or whatever, something that the other person can actually see or recognize. So an interesting one. So if you want to do some more work around looking up the Drake equation and stuff's kind of interesting. They do reckon that if you play with the Drake equation, and there's been some more research done around the Drake equation, there could be around 5,000 extraterrestrial civilizations out there. Kind of interesting number, right? But we haven't heard from any of them yet. So whether we will is kind of difficult to say. And we're also looking, as part of the effort for stars that have planets. The Kepler Space Telescope is one of the main space telescopes that we're actually using to do that. Now, interestingly enough, right, we have enough problem, seeing, well, we can see the stars, but we're certainly not going to be able to see planets around the stars. Does anybody know how we might be able to detect there's a planet going around a star if you can't physically see the planet? Anybody on chat? Gravity and light. Gravity, not sure. Light, yes. What about the light? Okay, going to give you another 10 seconds. And I'm going to tell you the answer. Light block. Yes, very good. So I got a little graphic. Here's the graphic. As the planet goes across in front of the sun, it blocks out, or in front of the star, it blocks out some of its light. So we're actually looking for these periodic dips in the output of light from the star. And from that, we actually infer the planet, its orbitary characteristics, and from that, we obviously infer whether the planet possibly could support life. Okay, right. And finally, like I said at the beginning of the presentation, I'm a member of the San Diego Astronomy Association. If you want to learn more about us, our website is at the bottom of the page. And of course, we're on Facebook and YouTube. All right, that's me, Anthony. I think this is where you get to take over.
Yeah, thank you so much for giving this presentation. I really enjoyed it. And to everyone else, thank you so much for coming. If you guys have a YouTube or a Gmail account, we'd greatly appreciate it if you subscribe to Gary's YouTube channel and our own YouTube channel at We Impact on YouTube. If you enjoyed this event and want to attend other STEM events hosted by We Impact, you can become a We Impact member here on the link which I put in chat, and there's a page which will show you all the future STEM events we have. And so thank you to everyone. That's all we have for today, and hope you all have a good Labor Day. Bye.
Cheers. Thanks, guys.